Okay, welcome to episode 7. So we have, I'm trying this out. This is kind of a new setup because I had to reinstall everything after I broke my Linux desktop. So hopefully this is working. You can hear me. As before, I'll try and keep an eye on the comments, but I also know that there's sometimes about a minute delay, so just be patient. If you ask a question, I'll try and answer it. But anyways, okay, Okay, so we've got a few things on the schedule for today. So over the holidays and such, I was working on a few interesting issues that I thought were interesting, so I want to talk about them today. One is this really weird bug where Caddy is generating gigabytes of logs with lock is stale messages, and that's not supposed to happen. So Mildred did very good due diligence in reporting the issue and giving us details and digging into it. And then Francis at some point suggested that it looks like there's an infinite loop that needs fixing, and he was right. And so I finally dug into it a couple weeks ago at the end of the holidays and determined kind of some ideas here on what to do. So we'll go over this. And then there was this fun bug that was reported privately from a sponsor who I'll be announcing later, hopefully. But this is an interesting one because it's really kind of obscure how Caddy does its listener management. So the way it manages sockets, because of graceful config reloads and such, we have a solution that works cross-platform, like on Linux and Windows and Mac, which is really cool. But also lent itself to kind of a weird bug that's actually been in Caddy 2 since the beginning, basically. And I'm actually not 100% sure on this fix. Actually, both of these problems, this infinite loop with the logs and this socket bug, they're both, this one, I'm pretty confident about this one, but I also wouldn't be surprised if there was actually still like a underlying problem that remains. And so we'll look at this in some detail and why it happened, what happened. But basically, the summary is that you would send your server a new configuration, and it would load and run your new configuration. But occasionally, some config reloads, this was very rare, but on some config reloads, even after a few reloads, the server would still be running the old config, like 2 or 3 configs ago, for some requests, but not all of them. So super weird. But I think my solution makes sense, at least it does in my head. Then again, would not be surprised if I was wrong. So hopefully we're right. It's a little tricky to verify this. The first one is fixed, but with a caveat, which I explain here later at the end. So we'll come back to that. And then finally, I want to give an update on the reverse proxy refactor, where we're adding dynamic upstreams. This is cool because you can basically tell Caddy which upstreams are available per request. And not only per request, but actually for each request there's a loop where the reverse proxy will retry if the backends are down. So it's every loop iteration actually that we get dynamic upstreams. And that's kind of interesting with regards to health checking, because some health checks have long-lived state and dynamic upstreams are not long-lived. So we'll talk about that. So anyway, those are my 3 things that I want to do today. I'll try and not make it super long. So let's dive in to the first issue here that Mildred reported a while ago about this infinite loop. So this is related to certificate management. And as you know, Caddy will use storage backends like the file system by default, but other ones as well that you can plug in, like a database or something, to store certificates and other TLS-related assets like OCSP staples, private keys, etc. But it also uses that storage backend to coordinate the management of those certificates. And so storage interface, like storage implementations, only need to implement a simple API, like put, load, or maybe it's store, load, list, delete, I think, and then critically, they have to implement lock and unlock. So the storage backend has to provide some sort of atomic operations. So let's look at this, shall we? Let's see. Okay. Woo, hello. So this is a diff of certmagic's filestorage.go. And this is the current filestorage.go. And you can see that basically file storage, you give it a path. And yeah, there's a few methods that it implements here. They're pretty simple: load, delete, list. It's just kind of a walk operation, stat. But lock, this is where it gets interesting. So again, this is Caddy's default storage backend. And let's see. Hopefully, is this big enough? If this isn't big enough, you can yell at me and I'll try and increase the text size. But so when Caddy goes to lock something, we have this loop here because what we need to do is we need to create a lock file. And file systems need to be able to provide atomic file creation operations. So there's a atomically create file. There's a flag you can pass called exclusion. I don't know. I think it means basically create the file only if it doesn't already exist. So that's perfect. That's an atomic operation, and so we can safely atomically create a file. If the file, so this file represents a lock. So if the file already exists, then the lock is already obtained, and we can't use it, or we can't obtain it right now. So if we got the lock, great, we can just return. However, if the lock file already exists, this is where it gets a little tricky. So there is the possibility that a instance, while it has a lock obtained, could... and in case this isn't clear, this allows multiple Caddy instances to coordinate and share resources and share and coordinate the management of certificates. So these locks, these files, these are all shared among multiple instances potentially. So if a lock file already exists, well, then we need to do we need to basically wait for the lock to become available. And but the tricky thing is that an instance could potentially obtain a lock and then crash and just shut down and leave the lock file there. So what we do in the file storage implementation is we actually have each instance routinely update the timestamp within a file. Hopefully this is big enough. I just got a comment that the font size needs to go up. So we routinely update the timestamp within a file every few seconds. And so if that timestamp gets older than a few seconds, then we know the lock is what's called stale. And that means that we can identify if a lock if an instance has crashed or something, and we can kind of ignore the presence of a lock, basically. Let's see, thanks Francis in the comments here. It looks like the meaning of excl is error if create and file exists, but the name is derived from exclusive, which is a bit misleading though, and causes many to misinterpret that flag. Yeah, I could see that, but it works for us. So anyways, what we do is we look for a stale lock file. So we open the file, and if we read the timestamp and see that it is stale, this is where the bug was. So if we look at the old version, which will be over here on the left in the red, all the deletions, what we used to do is we would delete it and try again to create one. So we would just remove the stale lock file, and this called a method called remove lock file, which is down here. And you can see I deleted it. But remove lock file would atomically remove the file, which is not an operation that file systems actually support. So what we would do is we would create an unlock file, which is an atomically supported operation in file systems. So we'd atomically create this .unlock file saying, hey, we are unlocking this right now. no one else unlock it. Because if two instances encounter a stale lock at the same time and just delete it, then if, for example, one of them begins to do that and the other one is like slower, let's say that one of them deletes the lock file and creates their own, then the other one deletes the lock file, thinking that they're the ones deleting it, and then you just deleted the new lock file that isn't stale. So this was why we implemented this in the first place. There's an issue here, number 7, insert magic, that discusses this issue. But basically, we would create this unlock file, and then, if another process was already unlocking, we would just return nil. This was the infinite loop, because what happened is apparently an instance crashed while the unlock file was present, which is only there for like a few milliseconds in theory. So very, very unlikely, but basically it left an unlock file there. And we don't do any of the fancy like stale lock checking and stuff, but you could imagine that if we did, we would also need a way to unlock the unlock file atomically. And it would just kind of keep its turtles all the way down. Because there is no, as far as I know, there's no atomic remove a file operation. And so anyway, this was the problem. If an instance crashed and left the .unlock file, then we would return nil here, which would just continue the loop, and you could see that we would have an infinite loop. And so that's not good. Also extremely unlikely, and this is the only time I've ever heard of it happening. But yeah, so how do you deal with that? Well, like I said, so here's that code again. If we try and atomically delete the unlock file instead of just like if we try and do stale unlock file checking and or try and basically it's just kind of turtles all the way down. Like I said, we'd create a .unlock file potentially. In practice, probably not, but it does get a little ridiculous. It does get a little recursive in theory. And so I just wanted to avoid that. And the only other option I could think of, honestly, was to, I just added a bunch of docs here, but basically the only other solution I could think of was if a lock file is stale. Now we're on the right here, we're reading the new code, which maybe we don't need the diff. Let me just pull open the current revision. So if a lock file is stale, you can see I revised it to just delete and try again to obtain the lock. So we would remove the lock, and yes, this is not technically perfect. Hopefully we can replace the lock file quickly, because if two instances come to this point and they both get into this case here, and one of them runs faster than the other. Let's say one of them removes the lock file and then iterates, you see here the continue, to create the lock file, and then the second instance finally gets around to removing the lock file. Well, it just removed the perfectly good lock file that it now thinks it has. So given how rare this is, especially, I don't know. I don't really know a better way to do this. I'm actually open to ideas here. We can discuss on GitHub if you would like to make a proposal, but I think this is better than an infinite loop. The potential for two instances to both think they obtained a lock. Again, not ideal. And there would be evidence of this, of course. You could see in your logs, and you could also see if you go to unlock the file and remove the lock, that one of them would return an error saying the lock doesn't exist because the other one removed theirs. So there would be evidence of this happening. It wouldn't create an infinite loop and deplete your system resources. So I still think this is better. Again, it is not perfect, and Caddy's storage backends are not intended for super high transaction volume, but we're okay with some degree of contention here. It's just that, yeah, so I don't know. I don't love this. but I also don't really hate it. Yeah, so I'm not sure a better way to handle that. But it does fix the problem. I think it just basically, we just document now that if, and this is actually up in the big go.doc comment at the top, so it's exposed in our documentation going forward, but basically if a lock file becomes stale, then the locking is now imperfect. It's a best effort, and it will probably be fine, but the simple solution is just to avoid the infinite loops and just try our best. So the best thing you can do is shut down your instances gracefully instead of a hard power cycle if you can avoid it, especially if they're very busy instances. But also, if in at least in the case of certificate management, if two instances do step on each other's toes, it's not the end of the world. Yeah, it's not great, but it's not the end of the world. So again, open to suggestions and feedback on this. If you want to open a pull request or a issue maybe first on GitHub to discuss it, that would be ideal. But yeah, I'm open to ideas here. Yeah, so this comment describes everything. So if you want to look at this, you can go to filestorage.go, insert magic, and take a look. Okay, so that was that issue. And you can see that at the end of it, I kind of give my thoughts here, and I was like, well, I don't know. It's probably a fine 99.99 for some number of 9% of the time. So yeah, there's definitely a caveat there, but oh well. So that's issue number 4448 in Caddy if you're interested. Okay, so this next issue comes from Caddy itself, comes from the listener's file in Caddy. So what would happen, gosh, actually I kind of want to pull open the old code here. Let me do that. Let me go to an older commit before fixing that. Browse files. Okay. Doesn't really matter which commit, just one before it. Okay, so Caddy listeners are really interesting because when you open a socket and you start listening on it, you can't open another. Typically, you can't open another listener on the same socket because it's already been bound. The OS, the kernel, won't let you do that unless you use some like OS-specific options. But we wanted something cross-platform, and anyway, we kind of looked at this issue because Caddy actually needs to have two listeners on the same socket at the same time, because when you do a graceful config reload, Caddy starts the new config before it stops the old config. Because if the new config doesn't work, it will shut down the new config and just leave the old config running. And so, zooming in the browser, there we go. Hopefully that's better. Anyways, so you have, for a short time, you have two listeners on the same socket. And so we solved this in a cross-platform way by kind of a weird little trick. So you need to be able to bind to the socket twice, but in reality we don't do that. We actually only bind to it once. So Caddy has this listen function. It's caddy.listen. You pass in the network and the address, just like goes net.listen. And basically, if the listener already exists, so we keep track of all the listeners we create through here, and if the listener already exists, we increment a usage counter and then we return the listener. So basically we're doing kind of reference counting. We are basically counting how many listeners there are for every address, and if the listener already exists, we just return the actual listener and increment a counter. So we make the callers of listen think that they are getting a brand new listener that's just for them, but we're actually sharing it. Well, sharing a listener obviously has a few problems. If you start two servers on the same socket, you can do this, by the way. You don't need the special hack here, but you could just create a listener and then start 2 servers, give them the same listener. You'll find that some requests or connections technically go to one server and some connections go to the other server. And so you'll see occasions, because they're both doing a for loop over accept on that listener, and sometimes one server will get it and sometimes the other server will get it. And so if you configure the servers a little differently, you'll see that some connections behave server A's way and some connections behave server B's way. And that's valid, it's just weird. And so for a very, very, very short time while configs are being reloaded, that kind of thing could happen. Now it doesn't, because when we do begin to shut down the old server, this kind of thing does. So when you reload the config, the new server is started, and for a very short time, the new server and the old server are both listening and looping on accept. And accept, by the way, is the function that I'll show you. Actually, I don't implement. Oh, I do implement accept. Accept is the function that's called in an infinite for loop, in a server loop, to give you connections. But anyways, so for a very short time, both the old server and the new server are accepting connections. Once the new config is guaranteed to be working, Caddy will shut down the old config, and will shut it down by calling server.shutdown, which in the Go standard library performs a graceful shutdown. It will stop accepting new connections, it will let old connections finish, and then you can set a timeout to forcefully close long-lived connections that are taking too long. So anyways, so that does happen, but ideally, again, you want to shut down the old server at some point. And this is where the bug was. So let me show you how this works here, and then I'll explain the bug. It's kind of obscure. So yeah, if the listener already exists, just return it. But if it doesn't, then actually call net.listen. So this actually creates a new socket listener. And we give it a usage counter. We're starting at 1. We store the listener in it, and we put that in a map, and then we return it. Now, you'll notice that we wrap it in something else called a fake close listener. So we wrap the listener in a global listener. This just means that it's shared among different users. And then the fake close listener implements a fake close method, and I'll explain this here. This is kind of where the bug was as well. So every caller to listen, even if they're reusing a listener, they get their own fake close listener with its own state. So that's kind of crucial. Listen packet is the analogous version of this for UDP. Okay, so fake close listener, basically its close method is a no-op. Virtually, it doesn't actually close the socket necessarily. And so here's how this works. When accept is called, so when the server is in its for loop and it's calling accept, then what we do is, even if the underlying socket isn't closed, we kind of keep some state as to whether it's closed, and we return an error if it is. But then we call the underlying accept, and now this is interesting. So if accept returns successfully, just return the connection, we're done. But if there was an error, now this is interesting because, and again, this code is really old, and this to-do is really old, but I'll show you why this isn't relevant anymore. And actually, this is kind of interesting because this to-do hints, this is where the bug was, actually, is right here, like these lines of code. And this to-do hints that there was something that I was a bit confused about or unsure about, but I kind of left it, and it ends up showing itself in kind of obscure ways later. It wasn't quite what I thought. Well, it kind of was. I'll explain this. So if accept returns an error, well, there was a reason it couldn't accept. So we don't really know what the error was, but it could be that the underlying socket was actually shut down, in which case we would know about it because we keep track of when the listener is closed. So if there was like a timeout error or some other thing, then we can know about that as well. So what we do is we check the fake close listener's state So remember, this is not shared state. And we check to see if the deadline has been set. I will explain this in a minute. If the deadline was set, then we clear the deadline by setting an empty time value. And then we set deadline to false, saying that the deadline is no longer set. And then if the listener was in fact closed, then we return an error. It's a fake closed error. And this is because we need callers of accept to break out of their accept. So yeah, let me explain how this works. Basically, you've got a server in its loop, and it's calling accept, and it's blocked, and it's waiting for the kernel to give it a connection. But if we want to shut down that server, we need to somehow get it to bump out of its accept loop even potentially without a connection there. So how do we do that? Well, we can close the socket, which again we can't do because another server has just started and is already using that socket, so we can't close it. So what we can do though is set a deadline in the past. And what this will do is it will cause callers of accept to return with a timeout error saying, deadline passed. And then the server the HTTP server in the Go standard library will see that it's a temporary error and will retry after just a couple milliseconds. A very reasonable amount of time, very reasonable cost. And that's a worst case scenario. But so what we do is we actually wrap the listener's close method. And this is where the trick comes in. We don't actually close the underlying socket. First, we check and see if it has already been closed, atomically, of course. And if it has not been closed, then we need to bump the accept calls out to get them to return. And so we do that by setting a deadline, and then we keep some state saying that we have set the deadline. And then we decrement the usage counter because, again, this server is done, so we decrement the usage counter, one less user of this socket. If it equals 0, then that means that no new config was loaded. We can safely close the socket for reals, so we avoid leaking resources this way. This is the only time we actually close the socket. Okay, here's the trick. So let's say that we're doing a config reload. The old server's getting shut down. It calls close on its listener. We don't actually close it. We set a deadline in the past. And then let's say there is still someone using the socket, so this code doesn't run. We skip this. So accept up here then is running concurrently, and this returns an error basically. And we can see, if fcl.deadline, so if we've set a deadline, then clear the deadline. Great, now the new server can use it and we're done. Like, everything's great, this worked really well, except thinking on this very hard one night after this bug report came in from the sponsor, I was scratching my head and realizing there's got to be either something wrong with config reloads. Like, why would Caddy be running the old config on some requests, but not all of them? But I looked at the config reload logic, and it was very simple and I think it's correct. And so I looked at the listener code then, because I remembered that I wasn't 100% sure about some stuff in the listener logic. And we do some funky things, because if this code is wrong and a server doesn't actually return from its loop when it's being shut down, then you would have that scenario where some requests are being handled by the old server and some requests are being handled by the new server. Even after multiple config reloads. And it sounds a little like a race condition, and it kind of is. So here's what happens, I think. Again, I might be wrong, let me know if I am, but here's what would happen. You've got two servers in a call to accept, an old one and a new one. Concurrently, close is called on the socket, but we wrap close, so we don't actually close the socket, we just set the deadline. Well, that should bump both servers out of their accept loops, or out of their accept calls. And they should both get a timeout error. What if, for whatever reason, only the new server bumps out of its accept call, and it'll return a timeout error. So if we skip this, we don't return a connection. But we go down here and we see fcl.deadline. Well, we know a deadline was set because close was called. And so we clear the deadline. And if we clear the deadline before the other accept call even sees the deadline, again, I'm imagining some sort of logical race condition, maybe in the kernel where there's like a polling mechanism and the kernel just didn't see the deadline was set yet. So anyway, then let's suppose that the deadline is set and cleared from the new server before the old server even sees the deadline, and therefore the old server just keeps on running. And so that's my suspicion. Again, this is a little tricky to verify, but I think the solution is as simple as just hoisting line 141 up to line 130. And that would make sense because the deadline boolean that we were using to keep track of whether a deadline was set is actually shared. The only thing that belongs to this listener only is the closed value. But the deadline is, of course, global to the whole listener because you can't just set it for one server but not the other. It's for the whole socket. And so that has to be a shared value. So anyway, I think what we need to do is make sure that only the fake close listener where close was called and thus set the deadline is the one that clears the deadline. And that way it guarantees that the old server has returned from its accept and guarantees that it's also the one to clear the deadline. That way the new server can keep running. And it might not even bump out of its accept with an error and wait a few milliseconds. It might just stay in its accept. It just depends on the kernel and the timing of things. So in the new code, well, here's the diff. I don't know if this is going to be... I simplified things a lot. You can see a lot of deletions. And I'll explain why I was able to delete a bunch of code. Yeah, that felt really good to delete all that. I did move some code down here, clear deadline and set deadline, but anyway, so let me explain to you what changed. So the listener code was one of the very first things that I wrote with Caddy 2, and it was before a type existed called a usage pool. I wrote a usage pool type later because I needed to basically keep global values through config reloads, state that needed to persist no matter how many times config is reloaded. And I have another talk on this on my Caddy playlist here on YouTube, but where I explain this in more detail. But basically, it's reference counting. A usage pool is basically, it's kind of like a thread-safe map. It's a thread-safe map that pools values based on usage. So you insert a value, has a usage of 1. Let's say that you insert the same value again, like during a config reload, it has a usage of 2. Let's say the old config is now unloaded, and so it cleans up by deleting the value from the map. Its usage stays, or its value stays there in the map, but we decrement the usage to 1. And then finally, when the last config is unloaded, the value gets decremented to 0 and is removed from the pool. And so we don't leak resources this way. We also don't step on toes this way. So the usage pool is really handy. We use it in the reverse proxy. We use it in a few other areas within Caddy. You can probably see here. Oh, new usage pool. Where's new usage pool? Yeah, we use it in the Acme server. We use it in the reverse proxy. We use it in logging. And now we use it in listeners. So we didn't have this before, and so what I did is I refactored the listener's code here. This is much shorter to use the usage pool. So we have a pool of listeners, and it does the reference counting for us. So it's really nice. We just say load or new. We basically create a string key for the listener. It's just a network address. And if that key already exists, then it will be loaded. Otherwise, this constructor function will be called, and we create a new one. So if the listener isn't bound to the socket, we actually bind the socket, and then we can return a shared listener. I just renamed some things too. you'll see that it's a destructor, which is just a way it can clean itself up when it's deleted from the usage pool. So it's kind of like our own little program space garbage collector, kind of. It's kind of an awkward type to work with, but it's really handy. But you can see the code is a lot simpler. Basically, get the listener from the global usage, or from the global listener pool. And it might be new, it might be not. We don't really care. Just get the listener. And then we just wrap it in a fake close listener. And by the way, the shared listener has a destruct method so that when it is finally removed from the pool, when it's no longer being used, let's say new config doesn't use that listener address anymore, we can actually close the listener, and so we don't leak resources. Okay, so then we do wrap it in a fake close listener like before, but you'll see that it's very simple. There's fewer fields here. We have a closed field, and we have a shared listener field embedded. Now the shared listener contains the underlying listener, the unique key, the string value, that just the address basically, and then whether a deadline was set. So that is the shared or global state pertaining to the listener, and then we have the local state pertaining to this like reference to the listener that each server gets. And all we need to keep track of is whether it was closed. And so you'll see the fix here. When we accept, yes, if the listener is already closed, just return. But if the underlying accept returns an error, instead of immediately clearing the deadline, we first check to make sure that this is the reference to the listener that was closed. In other words, the old server. If it was the old server, then we go ahead and clear the deadline and return a fake closed error. And this code is the same. Clear deadline and set deadline is the same as before. And so this guarantees that the old server is the one that will clear the deadline. So it guarantees that the old server had a chance to be booted out of its accept call. And therefore we can guarantee the old server is shut down. So yeah, that was, I feel actually pretty confident about this bug fix. It does seem to be working in my testing, and the user is going to be also verifying that in their environment. It's just one of those things that's really hard to like replicate, really hard. So it might just be a matter of time, and to see if it doesn't happen again in a reasonable amount of time, we will see. But some of you might have encountered this bug. I don't know. Sorry if you did. Is really obscure. I had heard of reports of this before, but when I asked for more information or details about how to reproduce it, people just kind of disappeared and went silent. So it was hard to figure this out. But this user has been really great to work with, and so I'm excited for this bug fix to go out pretty soon. Okay. So that is the obscure listener bug. Basically, we were letting the old server keep running, even through multiple config reloads. So yay, that's fun. Okay, the last thing is I just want to give an update on the reverse proxy refactor. So you know that for 2.5, we are refactoring the reverse proxy to support dynamic upstreams. And this has been going well. So for example, you might get your upstreams dynamically at every request from an SRV lookup at this address, for example. Or maybe you have multiple A or quadruple A records for a particular domain name. And so you can have Caddy look up those values at each request and have dynamic upstreams instead of hard coding all the addresses into your config. And then having to reload your config, which still is not a bad way to go, but if you already have something managing a list of available upstreams and it keeps changing and it doesn't know how to work with Caddy, then this is useful because your plugin can know how to work with that thing. For example, a console backend or something. But one tricky thing about this is health checks. Yeah, so health checks are fun because health checks obviously have longer lived state. This is fine for static upstreams that don't change, because if you have passive health checks that are counting how many requests fail or are successful or maybe are too slow, then that's something that you can just persist with the upstream. But the problem is, or if maybe you have an active health check too that is determining in the background on a timer that, oh, this upstream is no longer responding, market is down. So that's just a Boolean saying it's down with no other information, but you need to persist that, right? And so it's tricky with dynamic upstreams. And the other tricky thing was that we had implemented active health, well, I did. I take full responsibility here. I had implemented active health checks so that, so the way this works is if you have, let's say, 2 reverse proxy handlers in your Caddy config, and let's say they're for different domain names or different, I don't know, different something, but let's suppose that they both go to the same backend. Let's say you have active health checks configured on, I don't know, one of them, both of them, maybe configured differently, because you configure health checks per reverse proxy handler. But we were storing the result of health checks, so counting the number of fails, counting the number of requests, and and that Boolean that just counts whether the backend is available at all. We were storing it with a global instance of the host representation in memory. So each backend that you define becomes a host. So let's see if I can actually find that here. Reverse proxy. So I'm on head here. So this is without the refactoring. So you can see what it looks like currently. You can see that the upstreams, which are statically defined, are an upstream pool, and an upstream embeds a host value. So an upstream is a value where you have one upstream per reverse proxy handler. It's not shared across different reverse proxy handlers. You can have multiple, if there are multiple backends, but the point is they're not shared across different reverse proxy handlers that might be using the same address, like going to the same backend. So it might share a dial address, but the host, the underlying host here, this is a shared value, and we have a pool. The usage pool I was just talking about. So we use this in the reverse proxy so that we can keep track of state for a backend host that is the same, regardless of which reverse proxy handler is referring to it, or through config reloads, it can persist the state of the host, whether it's up, whether it's down, how many requests there are to it, how many failures recently. We can remember all that because hosts can live as long as there is at least one reverse proxy handler referring to that particular backend. So this is a global kind of deduplicated area, and the upstreams in the upstream pool are per handler, but they refer to the shared underlying hosts. So currently the underlying hosts, where was that? Host. This is all upstream host. So this is our implementation of the host interface, and you can see it would store the number of requests, the number of failures, and whether, so this is basically a Boolean, whether the host is healthy or not. So this is where the kind of a bug report came in, where you could have 2 reverse proxy handlers configured with active health checks for the same backend, but the active health checks were configured differently, or maybe only one of them had active health checks configured. You wanted maybe one handler to always use the backend, but the other handler you only want to use the backend under certain conditions. But if we store the active health check state or the results globally and we share that, then when the one handler's health checks decided it was down, then the other handler also saw it as down and wouldn't use it anymore, even though it didn't have that health check configuration, because it was shared. And so for active health checks, I think that made sense. And so, because this Boolean just says whether it's healthy or unhealthy. No reasoning about it, just that it's unhealthy or healthy. And so what I decided to do is move it into, I decided to move that so that it's not shared anymore. So now this is the code on the reverse proxy refactor branch. Now host is just a struct. I got rid of the interface. That didn't make much sense. Now the shared state consists only of the number of requests to the backend and the number of failures recently. And then each individual reverse proxy's handler, which has its own health checks configured, its own active health checks, and its own passive health checks, they can have logic on top of that. So they can both read the shared number of failures. Well, the active health checks don't. The passive health checks can read the shared number of failures, the number of requests, and then based on its configuration, like how many failures are allowed, how many requests are allowed, then per handler can still decide whether it's up or down. So passive health checks were not broken. It was just the active ones where, again, if we look at active health checks, you defined, where to send the request to and how often to send, because active health checks work in the background on a timer, and then you give it certain conditions, and then what active health checks will do active health check. So if it fails in any way, then we call set healthy false. But instead of that value being a global thing that's shared, it's only on this particular upstream that is not shared between handlers. So we fixed that. So now active health checks don't affect other reverse proxy handlers. And that's a really nice improvement. But here's the tricky thing with I just want to conclude here really quick. Here's the tricky thing when you have dynamic upstreams. This is all long-lived state. It's state that persists over many requests, and how do you do an active health check on a timer for an upstream that might only exist for a few milliseconds? So dynamic upstreams, you can see that in each proxy loop iteration, so basically here's serve HTTP, here's each HTTP request, we start the proxy loop, and the first thing we do is get the list of upstreams. It's either the static list or the dynamic list. And you'll notice the dynamic ones only live as long as this proxy loop iteration. Because at the end of the function, at the end of this loop iteration, we delete the hosts from the upstream so we don't leak resources. And so the answer I concluded was that dynamic upstreams don't get health checking. I think it only makes sense that whatever is giving you the upstreams dynamically is only going to give you available upstreams anyway. Because you can't get the list of dynamic upstreams and then what are you going to do? Do a health check before handling the requests? Or why not just handle the request and and then if it's down, try another one. It doesn't make any sense to do a health check first. Technically, you could benefit from passive health checking because, well, I'm not going to get into that in this stream. It's a little convoluted. But the documentation that I wrote, so these really long comments, they explain what I'm about to tell, or what I would tell you. So I'll just let you read those if you're interested. But yeah, basically dynamic upstreams don't get health checking in practice anyway. It doesn't make any sense for them to be health checked. Whatever is giving you the list of upstreams, whatever module that is, for example, an SRV backend, like this guy, serve upstreams, should only be returning available upstreams anyway. And so, again, you can still configure passive health checking with dynamic upstreams, as long as the upstreams that you get back are somewhat stable and they don't change all the time, they're not very different for every request, and assuming the server is busy enough to not like actually garbage collect the hosts for every request. So one way to do that is to actually specify your possible dynamic upstreams as static upstreams in your config directly up here, just like you do currently. And then the passive health check state can persist. But active health checks wouldn't work. Your passive health check state would exist, or would persist though. It's kind of weird. I don't know why you'd want passive health checking if you're already getting the list of upstreams dynamically. But anyways, it's been a busy few weeks. It's been good to work on this. So if you thought this was interesting, tune in again in the future. Follow me on Twitter. I look forward to interacting with you on GitHub, especially if you have questions or suggestions or ideas on how to do things better or differently. Feel free to open an issue, or you can visit our forum at caddy.community. We'd love to interact with you there. So thanks for tuning in.